So, thank you. My name is Markus and I want to talk about immediate feedback for security relevant code in IDEs today. This is part of our joint research project with RIX-IT, a provider of static application security testing tools, or more exactly one tool. And I want to start out with a bit of motivation for the project. So nowadays, no application or system gets by without worrying about security one way or the other. This is especially true for service-based systems and distributed systems, where security applies to encrypt, for example, to encrypting data at rest or in transit. Oftentimes, this encryption is realized through cryptographic libraries. For example, the Java cryptography architecture, JCA, or Bouncy Castle. These libraries are very complex and easily misused, and even a single misuse may leak data, sensitive information, or allow access to attackers. Two such bugs that were very prominent were Heartbeat in the OpenSSL library and Shellshock in Bash, both of which had devastating results and affected a large part of the infrastructure. One of these, the Heartbeat bug, is exceptional in that it was a bug within within the cryptographic library itself. Some prior research has found that about 80% of these bugs come from misusing the cryptographic library. To detect and flag such misuses, we have static application security testing tools, Sanitizer by RIX-IT, or the open source project CogniCrypt, originally developed at the TU Darmstadt and now part of the Eclipse Foundation. These tools are great and they can flag a lot of misuses and other problems that affect application security, but they have a few shortcomings, and these lead to their lacking adoption. I want to talk about two of these problems today. The first one being very long feedback cycles. In application security, we want to make sure that no problem escapes us, so we don't want any false negatives. Therefore, we spend a lot of time on analysis and perform very thorough and detailed analysis. This means that the tools are oftentimes not feasible to run on developer machines. Instead, we perform them as part of the nightly build, so developers code something, push it to a repository, and during CI or a nightly build, a build machine analyzes the code, creates a report, which developers get to see a few hours later or even days on the next day. This leads to problems that are common with long feedback cycles, one being that developers lose context information. So they finish some code, then they forget some of the constraints around it, and the next day when they have to fix some bugs in it, it takes them more time to get back into context and to fix the issue. And they might even introduce new issues because they don't get the full context back. Also, if you have a lot of code that gets analyzed, so if you spend a day writing out code and then the analysis runs, you might introduce a lot of problems, and you get a long list of problems which may overwhelm or intimidate the developers that are faced with fixing these. Another problem is that these tools and reports are not well integrated into IDEs, so users have to hunt for the location that's mentioned in the report. They can jump directly to the location, they have to find the file and the line. Changing the file or fixing other bugs might change the location, so this is also time-consuming and error-prone. And in the case that the analysis is running in a CI pipeline, changes to the code that are made between finishing the code and the analysis finishing might invalidate results again, so you have a report that does not reflect what you're seeing in the code base. And even if these tools are integrated into IDEs, some of them are are able to run on developers' machines, which some of them are, CoffeeCrypt being an example. They are often not integrated into IDEs, so they still lack the problem of context switches, and you still have to search for location manually. The second problem we see is that messages from SaaS tools are typically hard to understand. This is an example from an early prototype of Critical Mate, and here's data flow ended in a state that was not good. From this you cannot really find a problem. This is true for about 80% of the messages that Critical Mate pumps out, and it doesn't help you differentiate to identify the concrete error here. So these two issues make it hard to fix notifications from SaaS tools, and it may lead to users abandoning these tools or not using them in the first place, and this impacts application security negatively. So instead, we came up with Critical Mate, which is both the name of a project and a tool that was developed within this project. As I said, it was done in conjunction with the RIGS IT, and as part of the project, we developed a local analysis tool, Critical Mate. Another part of the project was the rule repository. So we had infrastructure for storing and exchanging rule sets between trusted entities and users. But today I want to focus on two key improvements that Critical Mate brings to static application security testing. The first one being shortening the feedback cycle. We integrated Critical Mate directly into numerous IDEs, and that way the results are presented directly in the code editor. So you write a line of code, Critical Mate analyzes it, and you see the highlight in the code, and you can get directly to fix it. This also gives us access to further IDE features, such as jump to location. So when you see a problem, in the problem list of the IDE, you can click on it and you're at the location of the bug. You get the context in the code editor. Also, the analysis is quick enough that we can rerun it whenever you change code, so you don't get same results. And you don't get long lists of issues because you can fix them as soon as they are introduced and they don't accumulate. The second way we improved it is that each, in addition to a brief summary for each issue, we create a long detailed view which can get interested users or less experienced users that don't know what to do from a brief summary the opportunity to learn about the problem. Each of these detailed views contains a compliant code example and a non-compliant code example. So a user can simply compare these two and see what he has to change or what they have to change in their code. There is an explanation of the problem and possible solutions down here, and there are further resources intended for beginners that are not yet familiar with the problem or with the space, so they can read up on the problem and solutions. And we have the opportunity for them to provide feedback, so they can flag unhelpful or false positive notifications, which helps us improve the analysis and notifications. So far for the stuff that we've done within the project, and now for a few opportunities to improve upon our results. The first one being adaptive static analysis strategies, and these could help us increase accuracy while keeping the feedback cycle short. The key trade-off here is that between speed on the one hand and accuracy on the other hand. What I mean by that is that usually we rely on heuristics to increase analysis speed, but these heuristics come with false positives. And by reducing the use of heuristics in situations where we can do so, which we could do through an execution time budget, we can increase the accuracy and reduce the rate of false positives while keeping within acceptable speed limits. One of that could be that when we have enough execution time budget remaining, we increase the granularity of analysis, or the detailedness of the analysis. a way to increase our execution time budget available is selective analysis. So instead of analyzing a whole code base or a whole file, we just analyze a single file or a single method, or even a single line or a single problem. And what can help with that too is iterative refinement. So we do a very inaccurate analysis first and just flag the issues where we're most confident that they're true positives. And then we spend time refining the issues where we're less confident to increase the confidence or reject them if they turn out to be false positives. The second area of adaptivity is adaptive notifications that can improve the understandability of notifications. This comes in multiple dimensions. So one is we can increase or decrease the amount of notifications that we show to a user. One idea here is, for example, instead of showing all notifications as soon as they're produced, we reduce the amount of notifications while the user is implementing a function or functionality. And for example, we might learn from their workflow using machine learning that they spend 20 minutes implementing a method or a piece of functionality, then they take a break, and afterwards they get to fixing issues. We can use these 20 minutes to analyze the code the user has written, and we can also use the break for that, and after the break we show them all the notifications that they were in this piece of functionality. It's still not as much as a nightly run would produce, and it's still, it fits with their workflow so they can fix issues when they're comfortable doing so. Another thing that we could do is increase the amount of detail that each notification entails. We're already doing that in parts, so experts only need to take a look at the summary and can already fix the problem. While intermediate users might need to take a look at the code examples, and beginners will also need detailed explanation and further resources. But we can also improve upon this design by learning or trying to learn how a user fits into his group. For example, for users users that are between beginners and intermediates, so they have some experience but not as much as an intermediate user would have, we can reduce the detail grade of the summary. Or for experienced intermediate users, we can increase the detailedness of the summary. Yes. Also, adaptation. We can adapt these code examples to a user's experience. So instead of showing a generic code example for one issue, we can take variable names and other properties of the source code from user's source code. So they become familiar, or the code that they see in the code example feels familiar, and hopefully it's easier to change and fix. And taken to the extreme, we can do this automatically. Once we know how to produce a compliant code example, we can apply the fix at user prompt automatically. This is already implemented in a few static analysis tools, not yet in the cryptographic space as far as I know. So, to summarize and conclude, CriteMate helps us shorten the feedback cycle of static application security testing tooling, and it improves the understandability of its results. And in the future, adaptive strategies can increase the accuracy while keeping the feedback cycle short, and adaptive notifications could improve understandability and actionability of the results further. Thank you.
Are there any questions? I have a short question. How do you generate the feedback? Do you use some form of knowledge base?
No, the analysis is data flow analysis.
Micro.
Oh, sorry.
So the analysis is a data flow analysis and data flow intent analysis. So we check we compile the code, use JVM bytecode, and the bytecode then is analyzed for calls, and these calls are built into call graphs, which are then fed through a state machine and simulated, and then we check that required ports are there. So it's kind of similar to evaluating a regular expression.
Any other question?
Before you leave, yeah. So before we leave, you're finished, huh?
Yeah, the last.
Okay, so before we leave, since a couple of years we have this SurfTech Young Researcher Award, and this year the Surf is covered by €500, right? For students it's fine, right? And for everybody it's fine. And this year's winner is Jan Schneider. So Jan, where are you? The picture. Here's the picture will be published at SurfTech and SOC and everywhere, so you will become famous. So congratulations, Jan needs to take a picture.
Schön blauen Hintergrund, das ist besonders attraktiv. Aber
Thank you very much. We reconvene tomorrow at 10 o'clock. See you. Thank you, Indika.